This presentation is delivered by the Stanford Center for Professional Development.
So last time we looked at this idea of just reachability. Reachability is the following state transfer problem. You start from 0, and the question is, where can you go? So it's a special state transfer problem. You start from 0, and you want to hit something like it's a point in state space at time t. And we said that R sub t is the reachable subspace. This is a subspace. If you can hit a point in t seconds or epochs, you can certainly hit twice the point, and it's a subspace. If you can hit one point, hit another, you can hit the sum. So it's a subspace. And it's a growing family of subspaces. So we'll know exactly what the family is. Actually, we already know for discrete time. For discrete time, it's interesting, but it's just nothing but an application of the material in the course. It's basically this. The set of points, R sub t, is the range of this matrix, CT. This is the controllability matrix at time t. I think I mentioned last time that this matrix you will see in other courses. It comes up in, for example, scientific computing. You'll see this, in which case RT is actually called something, it's called a Krylov subspace. So I may have mentioned that last time, but just so you know, if you will see this matrix doesn't come up in just this context. It comes up in lots of others. So this matrix here, I think we discussed it last time. As you increase t, it gets fatter and fatter. In fact, every time you increment time, the matrix gets fatter by the width of b. That's the number of inputs, which is m, is what we're using here. So what happens is you have a matrix. You start with b. That's where the range of b is where you can get in one step. Then the range of b and ab is where you can get in 2 steps. And that was parsed very carefully, and I guess I shouldn't have said it so quickly. When I said the range of b and ab, it means the matrix B space AB. So it's the linear combination. It's all linear combinations of columns of B plus columns of AB. That's where you can get in 2 steps together. Okay. Now we noted that by the Cayley-Hamilton theorem, once you get to n steps, a to the n is a linear combination of I, a squared up to an minus 1. And so the rank of CT, or the range, does not increase once you hit n, above n. So for example, the range of Cn plus 1 is also the range of Cn. So it doesn't grow. Okay. Now that means we have a complete analysis of, in a discrete time system, where you can get to starting from 0 in t epochs. The answer is just this. You can get to the range of CT for t less than n, and then after that, once you hit n, it's the range of C, period. So, and C is just Cn. That's called the controllability matrix. So and a system is called controllable if Cn is onto. So in other words, if its range is Rn. So that's the idea. And so you can say you get something that's not totally interesting. Not totally obvious. It's this. You have the following. In a discrete time system, any state you can reach in any number of steps can be reached in t equals n steps, period. Now, that doesn't mean that's a good idea. We will see why very shortly. But nevertheless, as a mathematical fact, it says that. It says that if you can't reach a state in n steps, then you can't reach it ever. So giving you more time to hit the state is not going to help at all. Okay. And the reachable set, that's the set of points you can hit with no limit on time, is simply the range of C. It's the range of this matrix. Okay. Now a system is called controllable or reachable. Now unfortunately, these have there are people who distinguish between reachable and controllable, sadly, and they don't necessarily have it. So sometimes controllable means something slightly different, but don't worry about it for now. A system is controllable if you can reach any state in n steps or fewer, and that's if and only if this matrix C is full rank. So that's the condition. And as you know, we'll just do a little stupid example here. Is this? You have xt plus 1 is this matrix 0, 1, 1, 0, x of t plus 1, 1, u of t. Now, we could just look at this and know immediately what it does. The dynamics does absolutely, it does nothing but swap the roles. It just switches. That's the swap matrix. I mean, if you ask me to describe it in English, that's a swap matrix. It simply swaps x1 and x2. The input, and this is the important part, acts on both on both states the same way. So the point is there's a symmetry in the system. I mean, it's just a stupid, simple example. There's a symmetry in the system. It basically says that whatever you can do to one state, and I'm arguing very roughly now, it will do the same thing to the other. And that's a hint right there that there's going to be some things you can't get to. We'll even see what they are. The controllability matrix is B. That's AB. And sure enough, BAB is not onto. It's singular. And the reachable set is all states where x1 is equal to x2, period. So in other words, no matter what you do here, no matter how you wiggle you will never reach a state that doesn't have the form of a number times the vector 1, 1, period. Just can't happen. And it's obvious here. You certainly didn't need, controllability analysis to see this here. And to be blunt about it, that's often the case in almost all examples. So, I mean, sometimes you don't know. You actually have to check. There'll be something. In fact, not only that, but most lack of controllability comes down to symmetries like this. They can be much more sophisticated in large, like mechanical systems and things like that, where after the fact, you'll realize that something's symmetric and your actuator configuration is symmetric. And of course, you couldn't do something after the fact. But that's what we'll see. Actually, there's a much more interesting notion of controllability that we're going to get to, a quantitative one. Okay. Now let's look at general state transfer. So general state transfer, that's a general problem. We're going to transfer from an initial to a final time, from an initial state to a final state. And of course, this is the formula that relates the final state to the initial state. And of course, this is completely clear. That's simply that's the dynamics propagating the initial state forward in time. That's nothing else. So this is, in fact, what would happen if you did nothing, if u was 0 over the interval. This is the effect. I stack my inputs in a big m times tf minus ti plus 1 matrix here, vector, sorry, and I multiply by this controllability matrix here. And this gives you the effect of of the input, how it changes your final state. Okay? So what this says is this equation holds if and only if I'll take x desired to be the state you want xtf to be. So I take xtf minus this is in the range of that, because this is in the range of that. And there's your answer. So it's actually, this makes a lot of sense. It's actually quite beautiful. It basically says something like this. If you want to know if you can transfer from an initial state to a desired state, then it's really the same as the reachability problem. What you want to reach is an interesting state. You don't want to reach x desired. You want to reach x desired minus what would happen if your initial state were propagated forward in time. That's what it comes down to. Okay? So this is simple, but it's quite interesting. So I guess let's say another way to say it is something like this. The u, if you want to transfer from t initial to x of t initial to some x desired, it says don't aim at x desired. What you do is pretend you're starting from 0 and aim for this point, which takes into account the drift dynamics. Okay? So that's kind of what you want to do. Okay. So general state transfer reduces to a reachability problem. And now I believe last time somebody asked the following question. We talked about reachability and your ability to get from one state to another, let's say over some fixed time interval. And the question is, if we made the time interval longer, can you get to more points? Certainly if the initial state is 0, that's true. If the initial state is not 0, that's false. It's just wrong. So it is entirely possible in general reachability to be able to hit a state from one initial state in 4 steps, but then in 5 steps to be unable to hit it. Okay? That's entirely possible, does happen, and so that's entirely possible. Now, there's a very important special case. Some people think of it as the dual of reachability, and sometimes people call this controlling. I mean, this is, if you distinguish between reaching and controlling, that's this, is driving a state to 0. So sometimes the problem of taking a state that's non-zero and finding an input that manipulates the state to 0 is called, some people, it's called regulation, and sometimes it's just called controlling. I can tell you the background there, that the basic idea in regulation is that x represents some kind of, your state actually represents, what we call x here, represents an error. It's an error from some operating condition. So you have some chemical plant, you have a vehicle, you have whatever you like. X equals 0 means you're back in some state that you want to be in some target state or bias point in a circuit or trim for an aircraft or something like that. And then regulating or controlling means there's been a wind gust or something's happened, you're not in that state, and you want to move it back to this standard state, which is 0, this equilibrium position, which is 0. And so that's why it's called the regulation problem or control problem or something like that. And here you can work out exactly what that is. It turns out here, this is just 0, so it depends on whether or not, and of course that's a subspace, so I can remove the minus sign here. What happens is it depends, if I give you a non-zero state, let's even just check that. So how would we do the following? I give you a system, I give you A and B, and I give you a non-zero state, and I ask, what is the minimum number of steps required to achieve x of t equals 0? That's the minimum time control problem, or whatever you want to call it. How do you solve that? So here's what you're given. I'm going to give you A, I'm going to give you B, and I'm going to give you this, x0. Now, how do we do it? How do I minimize t for which x of t plus 1 is, x of t is 0? Well, let's handle a simple case. If x0 is 0, then we're already done before we started. And the answer is t equals 0 in that case. Okay? How about, can you do it in one step? What do you do? You check. Actually, it's interesting. What you want to do here is the following. You want to check whether a to the t times x0 is in the range of b up to a t minus 1 b. That's it, I think. Make sense? So, I mean, this is what you need to check. And you simply increment t now to check. You try t equals 0. We just did that. You try t equals 1. So you hit a x0. You want to check if that's in the range of this. Okay? Now, if you test this and you get out to t equals n and the answer is still no, what do you say? Then it cannot be done. Actually, because of this term, that actually requires a little bit of argument, but that's correct. So that's the basic idea. I think we have a homework problem that's actually a more sophisticated version of this, I think. Good. Okay. All right. Okay. Now, again, just applying all the stuff we know, because it's nothing but applied linear algebra. There's nothing interesting here. It's just everything. It's just all the stuff we've done. Let's look at least norm input for reachability. That's actually much more interesting. So let's assume the system is reachable. Although actually, now that you know about SVD, it wouldn't matter if it weren't. But let's assume it is. And let's steer x of 0 to an x desired at time t with inputs u0 up to ut minus 1. I'll stack them in reverse time. That's just so I can use CT this way. So I stack them in reverse time. And I get x desired is this matrix. That's a fat matrix times this. This is my control. Controls stacked, or you could actually call this a control trajectory. That's a good name for that vector. I want to point out one thing about that vector. It runs backwards in time. Now, that's just indexing. I could have run them forward in time too, but then I would have had to turn CT around to start a t minus 1b, a t minus 2b, dot, 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 down to b. But everyone writes this as b, ab, a squared b. So time runs backwards in this vector. Okay. Now, in this case, C is square or fat, and it's full rank. So it's onto. And we want to find the least norm solution of that. The norm of this, by the way, is the sum of the squares of the norms of the components. That's true actually for any vector. If I take a big vector and I chunk it up, I divide it up, if I partition it any way I like, the sum of the norm squared of the partitioned elements is the norm squared of the original vector. So that's what this is. And you just want to get the one that minimizes this. This makes a lot of sense. Some people would call this the minimum energy transfer. That would be one. That's generally speaking a lie. It generally has nothing whatsoever to do with energy. Not only that, it's generally an objective. Uses an objective only because, well, we can do it. So it's extremely rare to find a real problem where the actual goal is to minimize the sum of the squares of something. They do come up, but they're very rare. Okay. Well, I mean, this is nothing. We know how to do this. This is just it's a fat full rank matrix. The least norm solution is this. It's the inputs. This is stacked running backwards in time. Is CT transpose CT, CT transpose inverse X desired. And that's it. So that's called the least norm or the minimum energy input that affects the given state transfer. And if you write it out in terms of what CT is, you get something very interesting. CT, of course, is B, AB, A squared B, and so on. And when you line that up with C transpose T, you get B transpose on top of, I guess, A transpose, B transpose, and so on. And when you put all the terms together, you get a formula that just looks like that. There it is. So that's the formula. And again, there's nothing here. You're just applying least norm from week 3 in the class. It's nothing else. But it's really interesting. First of all, notice that it's a closed form formula for the minimum energy input that steers you from 0 to a desired point in t epochs. And it just looks like that. And everything's here. I mean, the only thing in here is a matrix inverse. And you might ask, why do you know that that matrix is invertible? What makes that matrix invertible? This matrix in here is nothing but CT transpose. It's a fat matrix multiplied by its transpose. That is non-singular if and only if C is full rank. And in that case, it corresponds to controllability. Okay? You know about SVD now. So we can even handle the case. We can do the following. We can actually handle the case when the system is not controllable. And someone asks you, find me the minimum energy input to hit a state. So the first thing you do if the system is not controllable is you back off and you say, hang on, the system is not controllable. That means, by the way, that most states chosen you can't hit at all. Because the things you can hit lie in a subspace, but subspaces are small. If you pick a point at random, it'll be out of the subspace. So then the person says, I know, I want you to hit this specific point. You check if the point is in the range. If it's in the range of CT, you say, OK, I can hit it, and now I'll give you the minimum energy control that hits it. And the answer is embarrassingly simple. It's just this. It's CT dagger times X desired. It's that. Okay? That would be the minimum energy input. And that's, of course, stacked backwards in time over here. That would give you the minimum energy input in a case where the system is not controllable. OK. But in the case where it is controllable, C dagger is, in fact, this thing here. By the way, it's really interesting to see what some of these parts are. Let's see what they are. I mean, there's actually one very interesting thing is you see something like this. B transpose, I mean, there's sort of a transpose here. And the really interesting part is it's running backwards in time. So we don't have any more time left in the class, so I'm not going to go into more detail here. But it's just an interesting observation. By the way, this is related to things like you may have seen in other contexts. In filtering, you may have seen signal processing, you may have seen matched filters, which is basically where the optimum receiver is sort of the same as the original signal, but running backwards in time. So if you've seen that, this is the same thing. It's identical. So this is not exactly sort of unheard of. OK. Now, this is the minimum input. By the way, these are the things I showed on the first day. As I recall, you were completely unimpressed. So this is where we're just making inputs to some, I don't know, 16-state mechanical system to take it from one state to another in a certain amount of time. They were pretty impressive. We're just using this formula. I mean, absolutely nothing else. Just this. And all I was doing was varying t to see how long it, to see what the input would look like, to see what it would require to take you to a certain state. Now, one interesting, we can now say something much more interesting here. We can actually work out the energy, the actual 2 norm squared of this least norm input. Now, if you work out what that is, I mean, in general, what the least norm input is actually there's going to be a quadratic form. And the quadratic form is very simple. It turns out, when all the smoke clears, I'll just go through all this. When the smoke clears, it's this. It's a quadratic form. This makes perfect sense that the minimum energy, so this, let me explain what this is. This is the minimum energy defined as the sum of the squares of the inputs. By the way, this is the minimum energy. So this is the energy if you apply the input to hit that target state, if you do the right thing. You are welcome to use inputs that use more energy than this, and many exist. Well, actually, unless c is square, in which case, if you hit it, there's only one way to hit it in that, oh, and you have, sorry, c is square, which means there's a single input and t equals n. If c is square, there's only one way to hit it, so there's no, all inputs are minimum energy. But if c is fat, then real simple. There's lots, and you can go on a joyride and burn up a lot of energy and still arrive at x desired. So this is the minimum energy. It's a quadratic form. And that quadratic form looks like this. And it's actually quite pretty. Inside here, it's a sum of positive semi-definite matrices. Now, I know they're positive semi-definite because each term looks like this. It's a to the tau b times a to the tau b transpose, because that's, this part is just that. But whenever you take a matrix and multiply it by its transpose, you get a positive semi-definite matrix. That's what you get. So it's a sum of positive semi-definite matrices. Well, sums of positive semi-definite matrices are positive semi-definite. So, and in fact, you can even say this, and as a matrix fact, it's correct. When you increment t, you add one more positive semi-definite term to this positive definite matrix, once t is bigger than n, or at some point. And that makes the matrix bigger. And I mean now in the matrix sense. So this is a matrix here, which is getting bigger with t. And I mean in the matrix sense. That means, by the way, the inverse is getting smaller. The inverse is getting smaller. That means that the minimum energy required to hit a target in t seconds as a function of t can only go down. Well, it could be the same. In theory, it could be the same. OK, so, well, although actually normally it actually goes down. So, all right. So it's actually quite interesting here. It says that we now have a quantitative measure of how controllable a system is, or reachable. So reachable is sort of this Platonic view that says, can you get there at all? And this one is much more subtle. It's less clean, but it says basically this. It says, oh, I can get I can get to that state. No problem. I can get there. But what it'll do is it tells you if, for example, getting there is something that takes a huge amount of, a very large input is required to get there, then for all practical purposes you can say, I can't get there. Again, this depends entirely on the context. As to what's a big signal, of course, you have to know and all that sort of stuff. So that's the idea. But we could do beautiful things. I could ask you things like this. I could ask you, I could give a target state, and I could say that the energy budget is 10. And I could say, get what is the minimum number of steps required to hit this target and stay within my input energy budget? I could ask you that question, and you could answer it. You could answer it by incrementing t until this goes below 10. One possibility is this will never go below 10, in which case you announce that, well, you can announce several. You can announce that is too little energy for me to get there, no matter how long you let me, no longer how long you let the journey be. So that's one option there. So you can actually solve a lot of very sophisticated problems now. So what this does is it gives you a practical, it's sort of a practical, a quantitative measure of reachability, because it tells you how hard it is. It also allows you to say things like what points or directions in state space are expensive to hit. And expensive means require a lot of control. Cheap means you can get there with very little control. And it's quite sophisticated, quite interesting. You get these are ellipsoids, of course, and they basically show the set of points in state space reachable at time t with 1 unit of energy, if that's a 1. And I mean, it's actually quite sophisticated. It couples with the dynamics and things like that. Let me explain that. Or actually, let's go through the math first, and then I'll say a little bit about how this works. So as I said before, if I have t bigger than s, then this matrix, that's a matrix inequality is bigger than that one, because the difference between the two is the sum of a bunch of terms of the form, you know, FF transpose between time s and t. So that's what this happens here. Now you know that if one matrix is bigger than another, the inverse actually switches them. So the inverse is less than the inverse here. Now we're done, because if this matrix is less than that, then anytime you put z transpose z here and z transpose here and z here, this inequality becomes valid. This is now not a matrix inequality, it's an ordinary scalar inequality, and it works. And that says it takes less energy to get somewhere more leisurely. So that's the basic idea. And it all makes perfect sense. Now, I should mention something here. For general state transfer, the analog is false. Absolutely. It's just not, or is it? Ooh. Wow, and I put all that intensifier up in front, didn't I? Now, I think it's false. But all of a sudden, I had this panic. I'm not sure if it is. I think it's false. Let's just say that. That's what I think. I think it's false. I retract my intensifier at the beginning. So it's probably false. There we go. I'll leave it that way. So I think for general state transfer, it's false. OK. All right. So this is it? I have to think about that one for a minute. I'm pretty sure it's false. OK. Let's just look at an example. So here's an example. I mean, it's a 2 by 2 example, and because that's the only state space I can draw anyway. So here's a 2 by 2 example. And here's some system in increments like this. There's an input. And this is to hit, I want to hit this target state 1, 1. I just made it up. There's no significance to any of this. It's all just made up. And what this shows is the minimum energy required to hit the target point 1, 1 as a function of time. And you see a lot of interesting things here. You can see that, you know, if you hit it in 2 samples, it costs you an energy of over 9. If you say 3, you can get there with almost half the energy. I guess it's half the energy if you double. If you say instead of 2 steps, do it in 4, and so on. And you can see, and it goes down. Now what's interesting here is it appears to be converging. It appears to be going to an asymptote here, which means that to get to that point with infinite leisure still costs energy. Now I can explain that. That's actually reasonably easy to explain. If a system is stable, I haven't worked out the eigenvalues of this, or I don't know. Someone have a laptop open? So anyway, we'll get, if someone could just, or maybe, no, sorry, you don't even need a laptop. We could do this. Can someone work out the eigenvalues of this? For me, I need a volunteer. Can you do it? Do you have a pen? So he's working on the eigenvalues, which we'll get back to us in a minute. I put him on the spot. Sorry. We'll let you work on that for a bit, and then because it's just you have to write out a quadratic or something like that. Anyway, so the conjecture is that this is actually, well, no, I'm not sure what the actually cancel the eigenvalue thing. We'll see. It's going to be, I think if it's, what I was going to say is this, is if this is stable, then in fact, you have to fight, if a system is stable and you have to get somewhere, you actually have to fight the dynamics to take it out to some place. Because if you take your hands off the controls, it's very rough. If you do nothing, the state will just decay back to 0. So you're swimming upstream when you're doing reachability for a system that is stable. Okay? Now if it's unstable, let's talk about reachability. Let's say a system is violently unstable. So basically all the eigenvalues for a discrete time system have magnitude bigger than 1. What that means basically is if you do nothing, the state is going to grow step by step anyway. Now let's talk about what happens when I give you more and more time to hit a state. What's going to happen? What's going to happen? If I give you like 100 steps and you have a system that's highly unstable or just unstable, if I give you 100 steps to hit somewhere, what happens is all you have to do is push x of 0 away from the origin. All you do is you just push x away from the origin just the tiniest bit, and then take your hands off the controls, and you let the drift, which is the unstable dynamics, bring the system out to where you want to go. Does this make sense? So you kind of work with the fact. There you're not fighting the stream. It's actually on your side for reachability. Everybody see what I'm saying? So what that suggests is that for an unstable system, as you give more and more time to hit a target, the energy is going to go down. In fact, it's going to go down to 0. So we'll get to that now. All right. All right. So this is there's a picture showing like which directions are easy to get to in terms of input energy. Sure enough, the set of places you can go to in 10 steps is bigger than that. This ellipsoid covers that one. And it's not quite. It's actually twisted a little bit here. So, which again makes perfect sense. The other thing you see about these ellipsoids is the condition number is like at least 10 to 1 or something like that. And that means that basically, although the system is in fact controllable, it says the controllability or the reachability, at least in terms of measured by input energy, is quite anisotropic. It is not isotropic. It is very hard to hit target point like that. It is very easy to hit a target point like that. It's very cheap to hit this one and very expensive to hit that one. So the controllability properties are not isotropic in this case. Okay, so let's examine this business of this matrix of this energy going to 0. This is that's a sequence, as a function of t, that is a sequence of increasing positive definite matrices. And I mean increasing in the matrix order. That is a sequence of positive definite matrices which is getting smaller. Now, a sequence of positive definite matrices that are getting smaller at each step converges, just the way a sequence of non-negative numbers that are monotone decreasing converges. This converges to a matrix. That matrix has a beautiful interpretation. It's called P here. It's actually called the controllability Gramian, this matrix. And actually, it's the inverse of the Gramian, but that doesn't matter what it's called. So this matrix comes up, and actually, it's beautiful. It's a quadratic form that tells you how hard it is to hit any point in state space infinitely with infinite leisure. That's what this matrix tells you. Now, by the way, if the system is violently unstable, P can be 0. That's extremely interesting. So it takes basically 0 energy to hit anywhere in a system that is violently unstable. Let me just do a simple example. Let's take B to be I, and let's let A be 1.01 times the identity. It's a very simple system. U just adds to the input. The dynamics is you times equals the state at each step by 1.01. So basically it says if you do nothing, the state just grows by 1% each step. That's all that happens. It's a violently unstable system. All the eigenvalues are outside the unit disk. They're all equal to 1.01. And now it's completely obvious that the longer you take, you name any point you want to hit. Then what you do is if you take t samples, you go back, I guess, by 1.01. You actually find out what input is required to hit that, and you take that point divided by 1.1 to the t, and that's the u you've set on the first input. Now that's a sequence of inputs that just kick it out and then let the dynamics take it there. Those inputs will have, as t gets longer and longer, the energy will go to 0. By the way, if p is 0, it does not mean you can hit any point with 0 energy. The only point you can hit with 0 energy is the 0 state. So when you interpret z transpose pz, here, it's not, I mean, you'd say that's the energy required to hit it with infinite leisure. It's really a limit. It says that you can hit it, when this is 0, it basically says that you can hit that point, not with 0 energy, but with arbitrarily small energy by taking a longer and longer time interval. That's what it really means. Okay. Now it turns out if A is stable, then this matrix is positive definite. That follows up here. If a matrix is stable, well, what it means is its powers, that's a to the tau, are going to 0 geometrically. In fact, they go to 0 at least as fast as the spectral radius, the largest magnitude and eigenvalue of A, to the t. So that means this is a converging series. This thing converges to some positive definite matrix. The inverse of a positive definite matrix is positive definite, and you have this. So if A is stable, you can't get anywhere for free. But if A is not stable, then you can have a 0 null space. 0 null space means, well, it's just what we were just talking about. You can get to a point in the null space of P using U's with energy as small as you like. So that's it. And all you do is you just kick it a little bit and let the natural dynamics take you out where you want to go. You have to be careful doing this, obviously, but this is the way it works. So this is actually used in a lot of things. For example, it's used in a lot of what people call statically unstable aircraft. So if you see if you look at various sort of modern fighter aircraft, they'll look, sometimes, some of the really bizarre ones will actually have like the wings swept forward slightly. And it just doesn't look right. Well, it just looks like it's flying backwards, actually. And it just doesn't look right. And sure enough, it's not right. Because it's open loop unstable. That's what they mean by statically unstable. Most other ones are stable. Commercial ones are, at least so far, stable. I think it's probably they're going to stay that way, but who knows? So with like forward swept wings or statically unstable aircraft, you might ask, why would anyone build an airplane which basically sitting at a trim position in some flight condition is unstable? So I mean, let's think about what this means. It means things like your nose goes up, and instead of there being a force or moment that pushes your nose down, when your nose goes up, actually there's an up torque and your nose goes up faster. So I remember I know the eigenvalues on some of these things. Some of them are on the order, they're about 1 in the continuous time case. So that's e to the t. So basically your nose goes up in about 1 second, it's about a factor e higher. In 2 seconds, it's 9. And so someone even explained to me how they work. So first of all, why on earth would you ever do this? That's the first question. So actually, and this is just for fun. So someone give me a guess. By the way, I made a guess. My guess was totally wrong when I actually talked to someone who knew what they were doing. But,
so if you want to turn really fast, you can just turn a little bit and the thing will turn itself most of the way?
yes, that's the idea. You want to get a nice, snappy ride. Okay? But now, and you do. You get a very, as you can imagine you do, right? You pop your elevator down a little bit or whatever it is, and your nose, that's all. And your nose is now going to go very fast. Yeah, but you can do that. You can do that with a normal. So is the idea that what u is just, you can do it with a small u, so it's efficient? Okay. So what's the objective? So I assumed it was, I'm not, I don't know, had something to do. Anyway, I actually finally talked to someone who knew what they were talking about, at least on this topic, and they told me, in fact, why you do this. The main reason, actually, is it has nothing to do with efficiency or anything like that, obviously. The reason is the reason you want small control surfaces for smaller radar cross-section. So it turned out that was the actual reason. So the reason you want small control surfaces, you're obviously, if you're flying at Mach 2 or something like that, you're not really worried about energy efficiency or anything like that. What you want is a small control surface because control surfaces reflect radar stuff. So that's the real reason. Then actually I found out how they work. They have like 5 backup control systems. Because let's remember, you flip up, but you better be very careful with this, right? Because you flip up with a tiny, very small, little subtle control surface. It just goes like that. You flip up, but when you get to where you want, you better have just the right input to make sure you stabilize there and all that kind of stuff. Because if you lose it, I guess in this case it's all over. He said it's all over in 3 seconds. It takes 3 seconds is, before it's in under 3 seconds that whether the pilot likes it or not, the explosive bolts go and you're out. Okay, so that's the way it works. And the way it works is I think they said that they had 5 or 4, it was 4 redundant control systems. So I guess the first one fails, the second one state is already ready to go, the second one failed. If the fourth one fails, you're out the top, whether you push the button or not. So that's the way they said it. And they actually do this and stuff. And actually now there's a move to actually do this for some chemical processes too. Now, by the way, there's a name for a chemical process that's statically unstable. What would be the common name for it? It's called an explosive. Yes, that's correct. Yeah. So, so I don't know if these things are good or bad or whatever, but that's the and people are doing it, and they just said no. We operate at an unstable. We operate this process at an unstable equilibrium point because it's more efficient in terms of the overall operation. So that's it. So all of these obviously require active control to make sure everything's okay, right? Everything will become not, that's the whole point of an unstable system. Things will become not okay very quickly. There was a question back there. Maybe no? Just stretching. Okay, all right, so, okay. Let's look at the continuous time case and see how that works. It's a little bit different, but there's nothing here you wouldn't expect. And in fact, this allows me to kind of say something I should have said earlier, but that's good. Now I get the excuse to say it. To make a connection between the continuous and discrete time, there is a question. Right. Yeah. Ah, so it's a homework. I can't do the homework generally, just like that. I had a discussion once. I remember some people came to my office, and I started explaining something. 10 minutes, dead end. I tried again, dead end. Then after like 25 minutes, I said, do you think it's fair to assign homework that you can't do? And I said, yes, absolutely. Because I said at one point, clearly I could do it. And at that point, it obviously was trivial then. So, all right, so let's answer your question. What was it? We asked you to get good. I can try, but if I can't do it, I'm not embarrassed in the slightest. But go on.
The problem was a variation of what we just looked at for this.
Okay.
So you have to start at a certain point and go close to 0 but not to 0 with a minimum norm.
Oh, that's a good problem. Wow. Oh, I wonder who made it up. No, I'm kidding. Okay. All right. Okay, so you're given an initial state, and you want to steer it not to the origin, but to within some norm of the origin, with what? With a minimum norm input. That's a great problem. Right. Is it continuous time? Okay, fine. All right. So I don't know. Can you solve that? I guess you wouldn't have asked. I guess the answer is no. That was a rhetorical question. Well, let's talk about it, right? It's safer for me in case I can't solve it. So what happens is you want to, well, let's fix a time period, okay? So then it's a linear problem, right? As to where you can get. So I guess it's sounding to me like a bijective problem. Am I not wrong? Sounding to me like one, right? So the final state is what? Let's just say if you go t seconds, it's t epochs, it's a to the t x 0, right? Plus, and then something like ct times, I'm going to call it, I'll call it u, but everyone wants to understand u is really a stack of the times in reverse time. Is that cool? This is actually a sequence of u, a whole trajectory, right? That's what you got. And then what did you want to do? The condition is that this should be less than some number. What was the number I gave? 0.1. Good. A nice number. There we go. So we have that. And what did you want to do? You wanted to minimize the norm of u. And then your point is that we never did this, right? Is that your point? It seems to be. So we didn't do this. That's true. You can look through the notes and you won't find this anywhere. Any comments? What? Yes, thank you. Okay, so yeah, so we didn't do this. Absolutely true. This is a bi-objective problem. So basically here, except, this is, by the way, perfect example of how these things go down in practice, right? Because basically, you go back and look at week 4. It was all clean. It was like, yes, let's minimize, ax minus y, with small x. And then we drew beautiful plots and all this kind of stuff, right? Here, it's clouded by the horrendous notation of the practical application. In this case, the practical notation is steering something from here to there. So it doesn't look as clean, but it is the same. So you make a plot here, trading off, there's lots of ways. I can't remember how we did it before, but you would trade off these two things like that. And there's an optimal trade-off curve here. There we go. So one of them, I know one thing to do. You could set u equals 0. There, I got one. You could do nothing and run up a very small bill here. So how do you solve this? Anyway, I've already said enough. Are we okay now? So now what happens is you make the trade-off curve here, and then on this plot, what do you look for? I find the point here, which is 0. There we go, 0.1, and I go up here, and I'm looking for that point, and that'll solve it, right? Are you convinced? Yeah. Okay, so that's it. So, all right. So that was, it's true. You didn't do that before. But we did things that allowed you to do it. So, okay. Are you happy now? Okay, good. Okay. Let's do continuous time reachability. So how does this work? Well, it's a little bit, it's actually, in some ways it's trickier, in some ways it's actually much simpler. It's going to be interesting, actually. So here's the way it works. Actually, in some ways it's going to be uninteresting. That's the interesting part about controllability in the continuous time case. So, okay, all right. So we have x dot is ax plus bu. And the reachable set at time t is actually now an integral. And this, it's parameterized by an infinite dimensional set. It's the set of all possible input trajectories you could apply over the time period 0t. Absolutely infinite dimensional. Okay? Now it turns out that this subspace is super simple. It's just this. It's actually much simpler than the discrete time case. In the discrete time case, you can get weird things like this state you can hit in 5 steps, but not 4. This state you can hit in 7, but not 3. Or you can get all sorts of weird stuff. I mean, all the weirdness stops. Once you hit n steps, you can hit anything you're ever going to hit, you can hit. That's starting from 0 in the discrete time case. In the continuous time case, it just bumps up to anything you're ever going to be able to hit, you can hit. If you can hit anywhere, you can hit it in 1 nanosecond, at least according to the model. So it's basically this. You form the matrix B, AB up to AN minus 1B. That's the controllability matrix. And it basically says if this matrix is full rank, you can hit this set is all of Rn for any positive t. So it's really, in continuous time, it says basically any place you can hit, any point you can reach in any amount of time, you can actually reach infinitely fast. That's what it says. And this makes perfect sense. You just trade the size of the input for, well, you have to have your input act over a smaller and smaller time. And it really couldn't have been otherwise. I mean, it would have been really weird if there was a state here you could reach in 3 seconds, but not 2. That would have been kind of weird because you'd think, well, like, what exactly happened? And in fact, because that's a subspace, its dimension is an integer. And so had this other thing happened, it'd be like, the dimension of the reachable set would have, gone up at 2 equals, at t equals 2.237, it would have jumped from like 3 to 4. And you think, now, what on earth would allow you all of a sudden at some time instant to manipulate the state into some other dimension? I mean, it makes no sense at all. So in fact, it kind of had to be this way. So this is it. So that's the result. And we'll show it a couple of different ways. Actually, there's a bunch of ways to connect it up here to the discrete time case and see how it works. Now, one way to see that you're always in the range of C is simple. Let's start from 0. E to the TA is a power series. But I can use the Cayley-Hamilton theorem to back substitute powers of A starting at n, n plus 1, and so on. I can back substitute powers of smaller powers of A, sums. And I'll end up with this. It says that basically e to the TA is for sure, for any t, it is a polynomial in I, A up to an minus 1, period. It's a polynomial of A, of degree less than n. OK. Now, x of t is just this integral. But now I'm going to plug that in, and I get this thing. And now I switch the integral and the sum, and I get the following. It's the sum from I equals 1 to n of this. But that is just a number. You could actually work out what these are exactly, but it doesn't really matter for us. Because that's a number, and that's our friend, the controllability matrix. So what this says is, if you have a continuous time system, no matter what you do with the input, and you start from 0, you will never leave the range of the controllability matrix, ever. Okay, so that's, now we're going to have to show the converse, which is that any point in the range of the controllability matrix can be reached. First, we'll cheat a little bit, and we'll do that with impulsive input. So let's see how that works. Suppose the state, if we're going to use impulsive inputs, we have to distinguish between 0 minus 0 plus, well, t minus and t plus whenever t is a time when there's an impulsive input. So let's just say before the impulse, we're at 0, and we apply an impulse which is it's distributed across the inputs by a constant vector f, that's f1 through fm, and it's multiplied by this k differentiated delta function. That's what it is. And here, the Laplace transform of that is s to the kf. The Laplace transform of the state is si minus a inverse b s to the kf. I'll do a series expansion on this. I think that's called the Laurent expansion. Did I say that at the time? I don't think I did. No, I don't think I did. But that's what it is. I think we used it to do the exponential when you expand it in powers of 1 over s. But I should have said that, but I didn't. OK. So if I expand this, I take out the powers that are going to multiply the s to the k, and I get things like this. A bunch of them look like this. And let's look at this very, very carefully. When I take the inverse Laplace transform, these correspond to violent impulses in x of t. This S inverse is going to be the first one. That's sort of like a step term. It's something that just goes up to 1. The others, the constant, and so on, and all these, those are ones that are going to actually be multiplied by t, t squared, and so on. Okay? If I say what it is at t equals 0 plus, or some people call this the initial value theorem, however you've heard of it, it works like this. It says that that x of 0 plus, I mean, this is all the stuff that happens between 0 minus and 0 plus. This is what happens right after 0 plus. And then this is all the stuff that doesn't really get going until t is positive. In fact, at t equals 0 plus, it still hasn't even started. It's that. So that's what you get. It makes perfect sense. It basically says that if you apply an input differentiated k times, it has an immediate effect on the state. And the state is to move it to a to the k b. But now you know how to get, at least using impulsive inputs, we can transfer the state to anything in the range of c. Because if I make an input that looks like this, it's a delta function times f0 up to a delta function differentiated n minus 1 times fn minus 1. And I multiply this. If I apply this, then x of 0 plus is c times this vector, and now we're done. Now this says that at least using impulsive inputs, I can reach anything you can reach in any amount of time, you can now reach in 0 time using impulsive inputs. That's what this says. So that's the picture there. Now you can also do it using non-impulsive inputs. I think we'll actually get close to showing that in a bit, but I'm not going to show it here. So I think we'll just look at an example and see how this works. So we have two masses connected by a unit spring, a unit damper, and I can apply a tension between the masses. So I can pull if U is positive, and if U is, if U is positive, I can pull them together. If U is negative, I can push them apart. So that's the force I apply on these two things. So that's, here's the model. Its x dot is ax, and the states are the two positions and the two velocities of the masses, and here it is. The 1 minus 1 means, of course, we apply U. The force U is whenever we apply 1 Newton to one, we apply negative 1 Newton to the other. Okay. And the question is, can you maneuver the state anywhere starting from x equals 0? Is the system reachable? If not, where can you get it? Well, you can kind of figure out what it is, but just to kind of see, to do some of the calculations, we can actually work out what it is. There we go. To actually just calculate what happens, you work out the controllability matrix. It's A B, A squared B, and you get this matrix here. And you look at it for a little bit, and you'll quickly realize it's rank 2. That it's spanned, for example, by these two independent vectors. Okay. That was slang. By this set of two, this independent set of two vectors. There we go. That was not slang. Okay, so we get that. And you know, if you look at it closely, you realize it's telling you something that you should have known anyway, which is to say that if you apply a force internally to a system, you can't possibly affect the center of mass of the entire system. So x1 plus x2 is utterly unaffected, and x1 plus x2 dot, I guess that's x1 plus x2 and x3 plus x4 is going to be completely unaffected by applying an internal force to an object. Because if you apply an internal force, you can't possibly change the momentum of the object, the momentum, or have any effect on the position. And that's exactly what this says. So, I mean, that's just a stupid example to show you that how controllability in the Platonic case works, right? That, you know, the system's controllable or not controllable, and it's almost always just related to some symmetry or some principle from physics that you should have known anyway. So that's all it's doing. So generally speaking, when something's not controllable and you didn't know it, it's not something you should kind of go back and remove those files and things, remove the scripts that tested it, and just replace it with a note somewhere that says, obviously, it's not controllable because the center of mass, you know, blah, blah, blah. So that's what I recommend. Okay. So this is sort of what you'd see. This is a classical application of control. By the way, in some cases, it is not obvious at all, although, as I've told you many times, it is very important once you know it, once you know something, to claim, A, that it was completely obvious to you beforehand, and B, to make a good story that supports that. So I've seen cases where there'd be like buildings and stuff like that, and there wouldn't be it. You'd look at it, and it's like, I don't see any particular symmetry here. And then you'd work it out, and it would be uncontrolled, and there'd be some symmetry that's like not obvious. It'd be some weird thing where you flip the top half of the building into the bottom, and you look at it left to right or something, and there'd be some symmetry there. And even if there's not, you would say, oh yeah, there's a symmetry there. Someone say, really? And then if you say it fast enough and wave your arms around, that actually helps a lot, actually. Then they'll stop asking it. And then you say, well, can't you visualize that? And they'll say no. And you go, oh, sorry. Anyway, then you can look at the math if you like. All right. Let's move on to a much more important topic, which is least norm input for reachability in the continuous case. It's going to be very similar, except it's going to be kind of interesting now because it's going to be, we're going to have this possibility of actually effecting a state transfer infinitely fast. And that's going to come out of this. So let's see how that works. That's your minimum energy input. You have x dot is ax plus bu. And you seek an input that steers x of 0 to x desired and minimizes this integral here. Now, this is not anything we did before. These are not, in fact, this has got a norm. People would call this, by the way, the 2 norm, just the norm squared of u. Okay? But this is not anything you've seen before. When this was discrete time, u was sort of a stacked version, and it was big, possibly, but it was finite dimensional. That's an integral. This is we're in the infinite dimensional case here. Actually, it's not anything you need to be afraid of. Some of you, depending on the field you're in, will have to deal with infinite dimensional things. I mean, it might even just be in continuous time or something like that. My claim is actually, if you know all the material from if you actually understand the material from 263, None of the infinite dimensional stuff has any surprises whatsoever. Absolutely none. I mean, a few details here and there, some technical details. Everything we did has an analog in a simple, elementary one. Now, they'll dress it up and make it look very fancy because that's, I don't know, to justify the, I don't know, just to make it look fancy, right? But you'll see the concept of, for example, so instead of calling it something symmetric, you'll have a self-adjoint operator. So that's the other thing. So you can call it you're then welcome to call linear transformation an operator, which sounds fancy, but it's, or some people think of it as fancy. So you can talk about a linear operator, and you can find it, for example, a symmetric one can be diagonalized. I mean, there are some things that get more complicated, but if the operator is what's called compact, then it's going to be exactly the same. And you get an eigenexpansion, except everywhere where you have sum equals I equals 1 to n, it'll be I equals 1 to infinity. You'll have lambda I, qi transpose. I mean, it's going to look exactly the same. There's going to be something that the SVD also works, at least for compact operators. But I'm just mentioning this because some of you will go on there. If you ever have to do that, I mean, it should be avoided, of course, dealing with these things. But if you find you've already chosen or too deep into a field where these infinite dimensional things do, don't worry, because I claim if you understand 263, you can understand all of that just with some simple translations. There are a few additional things that come up that you don't. You'd have continuous spectrum and things like that. But otherwise, it's fine. Has anyone actually already encountered these things in something? I think there's a lot of areas in physics where you bump into these things. So, okay. All right. So this is your first foray into that. So let's just discretize the system with an interval t over n. Okay, and later we're going to let n go to infinity. So that's what we're going to do. So we're actually not going to look at first over all possible input signals. We're going to look at input signals that are constant over consecutive periods of length h, which is t over n. So that's what we're going to do. So we're not solving the problem. We're actually searching over a finite dimensional subspace of possible inputs, not all inputs. So we'll let them be constant, and we'll just apply our various formulas from various things. Turns out then that reduces exactly to what we had before. Now it's finite dimensional, and this is now the controllability matrix of the discretized system. And remember, these have formulas like AD is e to the HA, and BD is this integral here. Okay, and the least norm input, now this is all finite dimensional, so there's no hand waving, nothing. It's week 4 of the class. The discrete least norm input is given by this expression here. Now, if I go back and express this in terms of A, using these powers of these things, after all, A is an exponential, and powers of exponentials is the same as just multiplying this thing by that, you get actually something kind of interesting. What happens is BD turns into T over NB. So you get the following. Let's see. That's this expression here. That's this first expression here. As n gets big, that converges to something that looks like that. Now, this sum is nothing but a Riemann sum for an integral, and the integral is that. Now, you put these together. In other words, you take this thing and then multiply by the inverse of that. Notice that the n conveniently drops out. That just goes away. So does the t, for that matter. And I get a formula, and this is, in fact, different. It's this. It's B transpose times this A mate. By the way, this looks, if you compare this to the discrete time case, you will see that it is essentially the same. Well, you have to change integrals and things like that. Let's see if I'm going to be able to find it. I've lost it, but I put them in the wrong order. Let's see. Let's see if I even... I'm getting there. I think I'm getting there. Oh, I got close. It's 810, but these are all now hopelessly out of order, so too bad for me. Okay, I quit. I give up. Anyway, all right. This is exactly analogous to the formula for the discrete time case. What's changed is this. In the discrete time case, these are powers of A. But powers of A are not just powers of A. In discrete time case, powers of A has a meaning. It's time propagator. That's what it means. In continuous time, time propagator is an exponential. Actually, what's even more interesting is this. Look at this. If that time is tau, this is actually the system running backwards in time. which is this idea about matched filtering and things like that that we encountered earlier. That's this thing. This integral is what was, in the discrete time case, the following. It was something like this, A transpose to the tau. This thing looked like that. So maybe there's a t minus 1 or something here. Don't quote me on the exact index. But when it looked like that, it makes perfect sense. The integral has the sum has become an integral. Makes perfect sense. And this is actually time, that's time propagator. In B is the effect. So in fact, you can even say, I can even identify e to the t bar a b and say what it means. It's very specific. It's the effect of an input at a time on the state t bar seconds later. That's exactly what this thing is. And that's exactly what this is. It is the effect of a current action on the state tau samples in the future. That's what this is. And this is it. Now, what's really cool about this thing is the following. Now that it's completely and horribly marked up and no one can read any of it, but imagining that you could read it, the cool part is this matrix is non-singular as long as t is positive. I can make t 10 to the minus 9, and this matrix will be non-singular. Now, by the way, it's going to be non-singular, but if you integrate something, again, you have to assume some reasonable time scale and things like that. If I integrate something from 0 to 10 to the minus 9, that integral is going to be very small. So that says this inverse is going to be absolutely huge. And so what this says is, oh, I can steer the input, I can steer the state from 0 to a desired state in any number of steps. In any amount of time. I can do it very very quickly. But it's going to take a huge input. That's what this says. And that makes perfect, it all makes perfect sense. So it all goes together, makes absolute perfect sense here. Now in the discrete time case, you might want to know what breaks down. And what breaks down is real simple, and it's for a simple reason. Let's see if I can say this and not sound like an idiot. The problem in the discrete time case is that time is discrete. This is the problem. Here, time is continuous. I can make it as small as I like. But here, what happens is I'll decrease t. When t equals n, I'm still safe by Cayley-Hamilton. But the minute I drop t below n, then it is entirely, I can take t down, and at some point, this matrix can become non-singular, in which case the inverse doesn't work. By the way, if I replace the inverse with a dagger and make that a pseudo-inverse, you'd get something very interesting related to our famous homework problem. If I put a dagger in here, I'll get something really interesting. In fact, I don't even need all of this. I just put the dagger around the controllability matrix. What I'm going to get is going to be really interesting. I'm going to get you the least norm input that will get you as close as you possibly can get to the desired target. Did this make sense? So that's what C dagger will do. And that's not the dagger from lecture 4. That's not CC transpose C inverse C. Sorry, help me with this one. C transpose, whichever it is. C transpose quantity CC transpose inverse. Yes, that was it. It's not that dagger. It's the general dagger that requires the SVD. So that's what happens. OK. Now the energy required to hit a state is given by this integral. It's integral from 0 to t. And the cool thing about the integral is no matter how small t is, q is positive definite. It's invertible. And I'm not going to go over a lot of that, but that's sort of the basic idea. Let's see. And I'll just make the connection to the minimum energy over infinite horizon. The same story happens. I have an integral of positive semi-definite matrices here. If I increase the time t that you are allowed to use to hit a target, this matrix goes up, this one goes down, and that's the quadratic form that gives you, this is the quadratic form that gives you the minimum energy. So you have the same result again. OK, let's quit for today. For those of you who just came in, I think I announced at the beginning of the class, there's a tape ahead. It's today. It could well be, I know it's today, 4:15, Skilling Auditorium. But as usual, you cannot trust me, and whatever it says on the website is what it really is. And statistically, some of you should come, because otherwise I'd be put in the terribly awkward position of giving a lecture to no one. It's never happened. But hopefully this afternoon won't be a first. Okay, we'll quit here.